So let's now go to the inverse of a matrix. So what does that mean? What is the inverse of a square matrix? So it's only defined actually for square matrices. The matrix B is called the inverse of some other matrix A, as long as B times A is exactly this identity. So this square matrix which has ones on the diagonal and zeros off the diagonal. And if that happens, and we denote that matrix B, this inverse matrix, by A with a -1 as a superscript. So A, you might say A to the power -1 if you wish. So let's look at an example to make that clear. So if we have a matrix A, which is of this particular form, 1, 1 in the first column, 3 and 4 in the second column, then I'm claiming that this second matrix, which I call A -1, indeed is the inverse. So let's check that. So it's here on the slide, but let's also check that on paper. So I have this matrix A, and it's given by 1, 3, 1, 4, 1, 1, 3, 4, depending on how you read this. I'm claiming the inverse to this matrix is 4 -3 -1 1. So let me check that. So what I would like to check is that A -1, so this matrix times this matrix A is indeed the identity. So let's check that. 1, 3, 1, 4. First, sorry, I'm doing this wrong way around. So let me do it actually. Do this one, and then I'll do the other one as a second check. So 8, I'm going to compute A times A to the power -1, or the inverse of A. So this is A itself, of course. Now I'm going to use the inverse of A. 4 -3 -1 1. So let's check what the result is. What do we get? Top left hand corner. You get 1 times 4, that's 4, plus 3 times -1, that's -3, 4 -3, that's 1. Down here we get 1 times 4 plus 4 times -1, that's 4 minus 4, that's indeed 0. Up here we get 1 times -3 plus 3 times 1, again that's 0. And finally 1 times -3 plus 4 times 1, that's -3 plus 4 is again 1. So indeed, this is of course this identity matrix in 2 dimensions. So this is A times A -1, and of course, all as well, it should, this particular matrix, the inverse of matrix, it shouldn't matter on which side I do this multiplication. So let's check when that's actually true. So in general, if we switch the order of matrices, that does matter, but for the inverse and to a matrix and the matrix itself, it should not matter. So this special case actually. So let's check when that indeed also holds. 3, 1, 4. So this is A inverse times A. So let's again do this. 4 times 1 minus 3 equals 1. Minus 1 plus 1 is 0. Sorry, 4 times 3 is 12 minus 3 times 4 minus 12, 0. Minus 3 plus 4, that's plus 1. So it's again the identity matrix in 2 dimensions, this thing. So indeed, this matrix is indeed the inverse of this matrix. So we're right in coordinate A that is -1. And that's also what's written on this slide again. Why is this useful? So you remember when we introduced the matrices, I started out with this example of a system of linear equation. I mentioned we often have to, in economics or finance, or mathematics, you might have to solve these large systems of linear equations in unknowns. Typically those hopefully are square systems, so with n equations in n unknowns. we might have looked ourselves at two equations with two unknowns, but we can generalize this to n different equations, 1 to n, with n unknowns, x1 until xn. And remember these a11s, a12, etc. They were the coefficients in this matrix and in this equation, and I collected them jointly in this big coefficient matrix A. So and I argued actually that what we have here on the left hand side, I can briefly, or in short notation, I can actually write this left hand side as this matrix of coefficients with all the a11s up till a_n's multiplied by this column vector of the n-axis, and that the result of that should be equal to the right hand side here, which is a column vector of all the b's. So b1 until bn are collected into this column vector, which is called boldface b over here. So this was at that point just a way of writing, and we saw that this fits basically what matrix multiplication is. So I multiply matrix A by column vector x and I get column vector b. That's just another way of writing this system of equations. But suppose now that we know the inverse to this matrix A, to this coefficient matrix A. So we know what A to the -1 is, what this inverse to A is. What we can then do is we can actually multiply this whole equation here, ax equals b, which we want to solve, right? We want to know what x is. We can multiply that whole equation by the same thing on the left hand side and the right hand side. And what is useful to multiply this with? Well, actually by this inverse matrix. So I'm going to multiply both the left hand side and the right hand side with the same matrix A to the -1, and then still the equation should hold, right? But now this is going to be convenient, because what you see here is, if I look at this left hand side, I see here A to the power -1, or the inverse of A, times A times x. But since A inverse is the inverse of A itself, I know that A inverse times A is actually the identity. So I can rewrite this left hand side as the identity times x. I've also multiplied this column vector B with the same inverse matrix A, so that still remains here, so A inverse B. So I've rewritten, I just multiplied both sides by the same thing, by A inverse. But what this equation then writes to is the identity matrix times the column vector x equals the inverse matrix to A inverse, times this column vector B. But that's very useful, because multiplying anything with the identity, that's just like you're doing nothing to it, right? That's the defining character basically of the identity matrix. So the identity matrix times x, that should just give x. So that's what I wrote here. This is identity times x, that's just x. So it says x equals A inverse times b. But that's precisely what we want to know. We wanted to know what x is. So it turns out if we can somehow figure out, or given what the inverse matrix to the coefficient matrix is, then we can immediately solve this whole system of equation without having to blink our eyes almost. I say, oh, if this is the system, well, then the solution is obviously x equals the inverse matrix to A times B, by definition almost. So if we know what the inverse matrix to B is, we can just plug that in and compute. So let's see how that works in practice by looking at a small example. So the example here is this particular system of equations. So you can see it here already in matrix form. So let me go to the paper again and then write this first as a system of equation and rewrite it in this particular matrix form. Then I'm going to say, oh, somehow I'm going to give to you what the inverse of this particular matrix is, and I'm going to check that that indeed is the inverse matrix. And then we're going to use this rule to indeed compute what the answer is to that system of equations. So let's do all that again on paper. So let's start out with a system of equations, two equations, two linear equations, and two unknowns, 2 times x1 plus 5 times x2 equals 4. It's the first equation, and the second equation is 3 times x1 plus 7 times x2 equals 10. Now the first step is to say, oh, we can actually write this system of equations in matrix form. So what would that look like? What would that look like? Well, we collect these coefficients here, the 2, the 5, and 3, and the 7 in this coefficient matrix, be our matrix A, and we multiply that with this column vector of these unknowns that we want to solve for. What should the answer be? The right hand side. So it's again a vector here for that. So this was the translation of the system of equation into matrix form. Now the claim is, there's somebody who's telling you, oh, actually I know what the inverse of this matrix is. And the answer is, the inverse to that matrix is minus 7, 3, 5, minus 2 is the inverse of 2, 5, 3, 7. So this, I didn't tell you how we got here, but somehow we are told this is the inverse matrix. So that makes we can actually check. Is it actually true? Is that what? Does that indeed give the identity? Let's just check. I'm going to multiply this inverse matrix with the matrix that I started out with. See what it works out to. Minus 7 times 2, that's minus 14, plus 5 times 3, that's plus 15. Well, minus 14 plus 15, that's 1, right? Second of top right hand corner, minus 7 times 5 plus 5 times 7, that's minus 35 plus 35, that's 0, that looks good. At the bottom row, 3 times 2, that's 6, minus 2 times 3 is minus 6, 0. And finally 3 times 5 is 15, minus 2 times 7, minus 14, that's 1. So indeed, this matrix is the inverse of this matrix, which appears here. So, but now we can solve actually, because I told you, well, we start out with this system of equations. What I'm going to do is I'm going to multiply this whole system with the same inverse matrix on the left hand side and on the right hand side. So just write this out in full. Minus 7, 5, 3 minus 2, 3 minus 2, yeah. That's the inverse matrix multiplied by that left hand side here, 2, 5, 3, 7 times x1, x2 equals, and I'm also multiplying the right hand side by that same inverse matrix. Times the B matrix here is 4 and 10. That's so the column vector B. Now I notice that here we have this inverse matrix times the matrix itself. Because there are inverses, and we check that it's going to give rise to the identity. Well, the identity times x1. x2 will just give me x1 and x2. Is exactly this matrix times that vector. So let's work that out. What is that result? Minus 7 times 4, minus 28, plus 50, 5 times 10, minus 28, plus 50, I think that's 22. And secondly, 3 times 4 is 12, minus 2 times 10, so minus 20, 12 minus 20, that's a minus 8. So clearly, or apparently, the answer is, well, this system of equations that we had here, that's solved by setting x1 equal to 22 and x2 equal to minus 8. So let's just check that. If I compute 2 times x1, so 2 times 22 is 44, plus 5 times x2, so it's minus 5 times 8, minus 40, 44, minus 40, indeed that's 4, so that checks. And secondly, second equation, 3 times 22 is 66, minus 7 times 8, 7 times minus 8. So 66 minus 56, indeed that's exactly 10. So indeed, by computing this inverse matrix times this right hand side, we get actually immediately the answer. You know, what is the solution x1 and x2 to this system of two equations. So this is a fast way, or in this case not that fast perhaps compared to what you would have done in using the other way, but this is going to be a fast way if you are looking at very large equations and actually want to program this perhaps. We've seen that it works, and indeed it's going to work also for large systems, and that's the real power of using this forms of notations. The only thing here that remains is, you know, how do you find this inverse matrix? I just gave it to you just now. There are, of course, ways of computing this thing, not in a systematic way. I'm not going into. We're not going into that in this course, and you would learn that if you want to do a more advanced math course. But you know, typically, for the courses that you're going to do in your finance class, we're often is going to give you this, or you're going to use programs like Excel actually to compute such inverse matrices for large matrices, coefficient matrices. And next step it will be the transpose.